Thank you.
And now we have Kevin Leyton-Brown, Dominant Strategy Auction Design for Agents with Uncertain Private Values. This is, I think, Kevin's 17th talk here in Jerusalem over the past 2 months. So.
Thanks, Amos. So let me point out that this talk is primarily the work of David Thompson, one of my students who's here. So direct your really hard questions or happy comments about the talk to him. But of course, I'll be happy to answer your questions during the talk. And actually, I'm really glad to be able to give this talk right after Michal's very nice talk, because I think I'm interested in a very similar problem. So I'd like to start by re-examining a very strong, what I consider a very strong assumption from classical auction theory, which is that agents know their own valuations. And one way of thinking about Michal's work is that she's really thinking about a problem in which agents aren't actually sure what a good is worth to them. So the way that I got thinking about this problem is I just imagined myself in a real kind of auction situation. So imagine that I was to go to a foreclosure auction to buy a house or to buy a car at a police auction, something like this that I might actually do, which is a really high stakes thing. And I was sort of thinking to myself, I really would like for auction theory to be able to tell me something good in a case like this that might really matter to my life, so I can make some money. And so because it's a large purchase, I'm willing to think very carefully about my strategy, do some calculus if that's what it takes. But nevertheless, I get hung up very early because it occurs to me that auction theory asks me to identify some real value x such that if the house was offered to me for a penny less than x, I should be strictly happy to buy the house at that price. And if the house is offered at a penny more than that value, I should strictly prefer to keep the money. And in fact, if I look at the von Neumann-Morgenstern axioms, there's good reason to think that indeed there must exist such an x for me, or else there's really something wrong about the way that I think about money. So maybe I'm even prepared to believe that there really is such an x for me. But it sure doesn't feel to me like I can come up with what this number is. And it seems like a bit of a problem to have a model of how we should behave in an auction that presumes that I know something that in fact I don't know. So what I'm interested in is thinking about what impact it has on auction theory to take seriously this problem that at least I think that I have. So how can we model this idea that people don't actually know what things are worth to them? Well, I'll call agents with this problem that I've got deliberative agents. And I'll model them as having to pay a cost to learn anything to learn more than they sort of start out knowing about their own values. And then this decision about whether to learn about their values is going to be a decision in their strategy space that they're going to have to decide whether or not to take based on the expected benefits of taking the action versus the costs. So if I'm thinking about buying that car, I might take it for a test drive. It's going to take an hour of my time, but I might expect that it's going to teach me something about the car. And then I could take it for a second test drive and see if it's any different from what I learned in the first test drive. I could read an article online. I could read another article online. At some point, maybe I would decide to stop gathering more information, even if it would tell me more about the value, because I wouldn't expect that it was worth enough to me. Why might it be that I would have this kind of barrier between myself and my value? Let me just propose two reasons, which don't really only serve as motivation for the talk. The first is that it might just be that thinking hard is actually a costly thing for me. And in some sense, I'm boundedly rational. I know for me, thinking hard is pretty costly. I don't know about the rest of you. So it might just be that introspecting, just trying to work out really how would I feel in these different possible worlds is just kind of a costly thing for me. At some point, I'd be willing to just lose a penny versus thinking really hard. On the other hand, maybe as in some real auction domains like the FAA's aircraft landing slot auctions, maybe I actually need to solve a hard computational problem to figure out what my value is. If I win a good, I then have to figure out the solution to some optimization problem to know how I would then use the good. And so coming up with my whole valuation function might be difficult for me because I would have to solve many such problems. Anyway, that's all by way of motivation. How do we model such agents? Well, first of all, let me tell you a little bit about a very general model which we give formally in our paper, but which I won't give formally here because the details won't matter to the talk. Throughout the talk, I'm going to require that agents have independent and private values. By independent, I mean what you think I mean, that their values are drawn from some distribution. Private, in this context, means that no other agent, through their deliberations, can learn anything about my value. They can only learn things about their own values. So even under this assumption of independence and privacy, deliberative agents can be quite complex. So their set of possible deliberations can be very rich. The deliberations available to an agent may be conditional on things that have been revealed in the auction or on deliberations that they've previously performed. Deliberations may be noisy, so it may be that I can look at the car and I can figure, it seems like probably I like it more than $20,000, but I might just be wrong about that. I might be sampling from some distribution. It might be that all I can ever do is narrow in on my value, but I can never actually find it out perfectly, no matter how many deliberations I perform. Outside of this context of privacy, agents may be able to learn about each other's valuations as well as their own. This is something that has been studied in the literature, but I won't allow this. So I also want to tell you, I'll use this model in ways that don't depend on the details I haven't told you. It's also going to be useful to think about the very simplest possible model. So let me explain this one a little bit more formally. So I'll call a simple deliberative agent one who has two equally likely possible valuations. They can have the high valuation or the low valuation. These valuations are independent and private. Of course, everything is common knowledge, so the agent knows the expected value of his valuation before deliberating. And at any time, the agent can pay a fixed cost and discover his valuation perfectly. So this agent never would have to deliberate more than once. The deliberation is perfect, and there are only two possible valuations. So some background about this problem. I guess as far back as 11 years ago, Sandholm started thinking about these kinds of auctions and showed that second price auctions don't have a dominant strategy. In some past work, which won't be the focus of this talk, Dave and I looked again at second price auctions and showed that, in fact, they don't even have symmetric pure strategy equilibria. So their only symmetric equilibria are, their only pure equilibria are asymmetric. Let me give you just an intuition for why that is, because it helps you to think about the domain. And I'll do this in that simple deliberative setting that I told you about. So you can think about the setting as starting out with nature choosing for the agent the value, one of two possible valuations, the high one or the low one. And just to make the numbers work out in this example, let's make the high one 4 and the low one 0. And the agent starts out not knowing which state he's in because he doesn't know what valuation he has. The agent then is given the choice of whether to deliberate or not to deliberate. And if he deliberates, he'll be able to distinguish which state he's in. And if he doesn't deliberate, he won't be able to distinguish. Then the agent is allowed to decide on what bid to submit in the auction. Remember, this is a second price auction. And then a whole bunch of other stuff happens. Everybody else decides whether they're going to deliberate or not, places their own bids. The tree gets really enormous, and I'm not going to draw that part of it. And then at the end, some payoff is realized. So because it's a second price auction, it turns out that the bidding part is still simple. So as Michal said, you should bid your expected value in a second price auction when there's nothing else that you can do. So if you know what your value is, well, then you should bid your value. So this guy should bid 4. This guy with the low type should bid 0. And these guys who didn't deliberate should bid the expected value, which is 2. And so now the question is, should you deliberate or not? And we can take this problem and kind of induce this normal form game here for the case of two agents and the two values that I showed you. Now, all these numbers look kind of similar, but they come from different places. And the game doesn't have to be this symmetric if I had picked different numbers. But what does always happen is that we get strict equilibria on the off diagonals here, saying that I want to deliberate if you didn't deliberate, and I want to not deliberate if you did deliberate. And the reason is that the very best thing for me is if you deliberate and I don't, because we can separate from each other without my having to pay the cost of deliberating. And so that's intuitively why there's this miscoordination game. Even though our values are independent, our expected values start out being the same, and we can separate from each other if I find out what if you bid differently from the expectation, and that can give me essentially the benefits of deliberating without the cost. Yes, the cost is C in this example. So we can look at where these numbers came from. That's why I put this here. So for example, in the case where both of us deliberate, there's a 1/4 chance that we both have the high valuation. So we're both going to bid 4.
But our Bayesian distribution is the same for the agents?
They're independent. We have two, in this example, uniform distributions. Pardon me?
Identically distributed?
Yeah, we're independent.
Independent, but identically distributed.
We would be able to extend this easily enough, in this case, to non-identical distributions. But in this example, recall the simple deliberative setting that I gave, which I claim is the simplest thing I can have, is uniform for everybody. So that's what this example is considering.
But what I'm saying, if I have a small range and you have a big range, whether I should deliberate or not has nothing to do with you. You have a much more precise range. Why should I care whether you have
That's fine. I'm really trying to show you one example here. I think I see where you're going, but this isn't even really the focus of this talk. So let's take the rest of that offline. But what I want to point out here is just that it's good for me if you deliberate and I don't. So my strategy about whether or not I should deliberate, at least under the valuation distributions that I'm speaking about here, it caused me to care about your value. That's kind of intuitively why we don't have a dominant strategy in this auction. And in fact, things aren't even symmetric unless we play a really inefficient mixed strategy equilibrium. Similarly, other people have shown that Japanese and eBay, by which I mean ascending proxy auctions, don't have dominant strategies, and that neither of them is equivalent to second price. So what else is known here? So it seems like this situation is pretty complicated in these auctions. A lot is known about Bayes-Nash implementation, or relatively a lot. So it's been shown by Bergman and Valimaki that the second price auction is the most efficient among sealed bid auctions, and that it's strictly worse than the Japanese auction. Cavallo and Parks identified the social welfare maximizing single good auction. Relatively less is known about dominant strategies, particularly because of an influential impossibility result due to Larson and Sandholm, which considered general, not restricted to IPV valuations. And this leaves open the question of if agents are restricted to IPV valuations. I'll tell you a little bit more about this later, but essentially, under a bunch of properties that you would want, it's not possible to have any dominant strategy mechanism in a deliberative setting. So the question that I'm interested in this talk is if agents are restricted to IPV valuations in an auction setting, which, if any, single item auctions offer dominant strategies. So I'm interested in characterizing the set of dominant strategy auctions for this setting. So if I want to do a characterization, it's natural as a mechanism design person to think about a revelation principle. That's kind of the tool we use to be able to look analytically at the space of mechanisms. And unfortunately, in this setting, things are a little bit different because direct mechanisms can't simulate indirect mechanisms. The mechanism can't simulate the results of a deliberation for an agent because the mechanism really doesn't know what the agent's value is. And neither does the agent. Only by paying the cost and finding out their value does the agent figure out what their valuation is, or figure out whatever information they can find out. And furthermore, agents' decisions about whether to deliberate or not can be conditional on other things that happened earlier and on information that was revealed to them. So we can't just ask the agents to do all possible deliberations up front, give that to us, and then run the mechanism. That would ask everyone to pay costs that they might, in equilibrium, not want to pay. So for this reason, Larson and Sandholm concluded that you can't use revelation principles in this setting. And in fact, they showed their negative result without appealing to a revelation principle. That's a problem for us, though, if we want to characterize. So we went back to this question and indeed are able to show that it is possible to recover a revelation principle here in a relatively standard way if instead of holding ourselves to direct mechanisms, we instead think about dynamically direct mechanisms. So what do I mean by a dynamically direct mechanism? These are mechanisms that ask one agent to deliberate, to report the result of deliberation, and then potentially pick a different agent, ask them to deliberate and report the result, repeat this process as many times as they like, and eventually choose an outcome. So this mechanism is not direct in the sense that it really has to interact repeatedly with the agents. But it is direct in the sense that the only things it ever asks the agents to do are simply to perform deliberations and report the results. So kind of like a direct mechanism, the language is about valuations and types rather than being about some arbitrary strategy space. So let's think about how an indirect auction looks in this setting. This figure essentially follows Larson and Sandholm. So we have some indirect auction mechanism which from time to time makes information available to a bidder, gives that bidder an opportunity to place a bid, and then that bidder's strategy determines whether or not to query their sort of hidden information source, which comes at a cost. If they query their information source, they receive an observation, or maybe they don't do that, and then they make a bid, and this whole thing proceeds over and over again. So the mechanism provides information to the bidders. They may or may not bid, and if they bid, they may or may not query their information sources to learn something. So intuitively, the way our revelation principle works is to kind of in the standard way draw a box around this whole thing to make a dynamically direct auction, but we still have to kind of have queries hanging off it for the bidders. So what we can say is we're going to simulate the strategy of the agents, as the revelation principle typically does. But in the places where the agent's strategies tell them to query their information sources, we're actually going to go off to the agents and invite them to perform those deliberations for us. So that's what I mean by a dynamically direct mechanism. At this point, I hope the revelation principle proof is pretty clear to you. Just to state it a little bit, state a couple of definitions that will be useful to me. I'll say in this kind of a setting that a truthful strategy is one in which an agent deliberates when asked and reports the result of that deliberation truthfully after having performed it. I can't really mean that truthfulness means that you tell me your value because you might never know what it is. A social choice function in this setting is a possibly randomized mapping from the true valuation profiles, which we might never find out, to allocations. And then our revelation principle for deliberative agents says if I can implement a social choice function in dominant strategies, then I can also implement it in truthful dominant strategies using a dynamically direct mechanism. And this revelation principle holds even for our very general IPV model that I told you about earlier, which I didn't define formally. OK, so now let me get to my main question about trying to characterize which mechanisms offer dominant strategies in these kinds of settings. So no mystery here. The answer is going to be yes, there are dominant strategy mechanisms, and they're the sequential posted price auctions. So let me define those. So a sequential posted price auction is multi-stage, and at every stage, the auctioneer makes a posted price, take it or leave it offer to one agent. So I'm going to go to one person, I'm going to go to Amos, and I'm going to say, the good could be yours for $7. Do you want it or not? Amos can decide whether or not he wants to deliberate. He can take the good or not take it. And then if he takes it, I just give it to him, and that's the end of the auction. If he doesn't take it, he's out of the auction forever, and I pick a different person, and I continue this process as many times as I want. So our characterization theorem says that a deterministic social choice function is implementable in dominant strategies if and only if it's implementable by a sequential posted price auction. So let me tell you about the proof. So the proof for the if direction, saying that sequential posted price auctions offer dominant strategies, is quite straightforward. Because agents' values are independent and private, the agent who's currently being offered a price doesn't care about anything that could happen after him because of independence. And he doesn't learn anything about what happened before him because he knows the mechanism, and even just the fact of his selection tells him everything that he could learn, and anyway, everything's independent. And so in a very strong sense, we can change all kinds of things about the model, and we hold on to dominant strategies here. So even in our very general IPV model, we maintain dominant strategies here. For the only if direction, things are a bit more complicated, and that's what I'll speak about for the rest of this time. And here, so these evens are a little bit confusing. Here, because this is a positive result, proving it for a big class is a stronger thing to do. Here, because this is a negative result, proving it holds even when I restrict myself to a small class is a stronger thing to do. And here, even under my simple IPV model, it remains the case that the only thing that works is SPPAs. So let me tell you about this only if proof. So why are sequential posted price auctions the only mechanisms that offer dominant strategies in deliberative settings? I'm going to assume that I have some truthful, deterministic, and dynamically direct mechanism that implements some social choice function. I'm going to assume that my agents have the simple IPV model. And I'm going to show that this same social choice function is implementable by a sequential posted price auction. So my first lemma is pretty straightforward. I'm not going to prove it. It says that the outcome chosen by the mechanism must be completely determined by the types of the agents who deliberate. So I can't have a social choice function that distinguishes between agents who in equilibrium don't deliberate, because there's no way for the mechanism to tell those guys apart. This lemma is more important. This is really the crux of the argument. And Dave and I call it influence. So the idea here is that an agent will only deliberate. Bear in mind here we have dominant strategies. So it's a dominant strategy for an agent to deliberate only when doing so always makes the difference between winning and losing. So that is, you're only going to deliberate in a situation where when I give you a situation where there's one thing you could say that would cause you to win, which is declaring the high type because you have only two types. And there's another thing that would cause you to lose. So why is that? Well, otherwise, for some strategies of the other agents, either you would always win or always lose. And that means you're being asked to deliberate, but you wouldn't do it. You would just declare something, and the same thing would happen, but you wouldn't pay the deliberation cost. Or you would lose with the high type and win with the high type, and that violates dominant strategy truthfulness. Now, I'd like to point out here that this proof does rely on our assumption that the mechanism is deterministic. So now I can tell you kind of the rest of the structure of the proof. So let me consider how my social choice function will, what answers it will give me as I give it different inputs. And let me start by considering the case where everybody has the high type. So recall my social choice function is defined on the true values of the agents, even when I don't know what they are. Although information availability tells me that it has to say the same thing in all the cases where people, in valuation profiles that differ only in people who didn't deliberate. So in this case here, what could happen? Well, either nobody's going to win here, or some arbitrary agent is going to win. So in the case where nobody wins, it's very easy to see that I have a trivial sequential posted price auction where just nobody ever gets to win the good. So let's instead consider the case where somebody wins, and let me just call the guy who wins agent 1. So now let me consider this case, where agent 1 wins. Well, by the influence lemma, all of these other guys with the high type here can't possibly be asked to deliberate, because agent 1 is always winning in this case. And so it must be that in this case, where agent 1 has the high type, and we don't know what types anybody else has, they have any type, in all of these different valuation profiles, the social choice function always has to make agent 1 win, because otherwise we would have a violation of influence. By information availability, the mechanism has to set agent 1's price independently of all the other agents' valuations, because it does the same thing in all of these cases, and it doesn't know what valuations they have. And by dominant strategies, it also has to set the price independently of agent 1's valuation. So agent 1 has to be presented a price that depends on nobody's valuations, and that makes it a posted price. Now let's consider this case. So we have the same agent 1 now has the low type, and everybody else has the high type. So what might the mechanism do in this case? Well, here again, it might be that nobody wins in this case. The auctioneer keeps the good. It might be that agent 1 wins again. Or it might be that some other agent, without loss of generality, let's call him agent 2, wins in this case. Well, in the first two cases, we again trivially have a sequential posted price auction. So let me speak about this third case where somebody different wins. And here, essentially, we can make a pretty similar argument, but let me do one more step of it. So when agent 2 wins here, then by influence, the social choice function, again, can't depend on the valuations of anybody else, because we couldn't ask them to deliberate. By information availability, his payment can't depend on these values. And so by dominant strategies, it also can't depend on 2's valuation. So again, it must be that agent 2 is being presented with a posted price here. And we can then proceed by induction and come up with the fact that at every step, somebody has to be presented with a posted price. So let me discuss a couple implications of this result. The first is that it's nice to see that it's possible to circumvent Larson and Sandholm's impossibility result when we're in the IPV setting. So for those of you who know about the result, we're able to satisfy all of the things that they say we should want that make sense under the IPV setting. One of the things that they say we should want is that agents should not be able to gain by deliberating about each other's valuations, and that's not something that makes sense in the IPV setting. Secondly, I think it's interesting that our result adds sort of another data point in favor of recent arguments that have argued for sequential posted price auctions. So I think it's striking, and maybe this echoes some points that Ishai was making yesterday in his talk. It's striking that posted price mechanisms occur very often in practice and seem to be really important mechanisms in the world. There's also a whole string of recent papers from this community showing that these auctions have good revenue and efficiency properties, and they're good for limiting the amount of information that's revealed. So there seems to be kind of this accumulation of evidence saying that there are kind of appealing things about sequential posted price auctions. None of this work was concerned with this problem of agents not knowing their valuations, but in this setting as well, these really seem like the good mechanisms. So to conclude, I've described a model of a single item auction with deliberative agents who have to pay to learn about their IPV valuations. And we have two contributions in this work: a revelation principle for this setting, which uses dynamically direct mechanisms, and a characterization of which mechanisms have dominant strategies in this single good auction setting, which are precisely the sequential posted price auctions. Some interesting open questions that Dave and I are actively thinking about, partly with Anna and some of her colleagues, are maximizing revenue or welfare in these settings, looking at more general domains, so going beyond single good auctions, and looking at randomized mechanisms where indeed it is possible to do a little bit more than I showed you here. So thanks for your attention, and I'm happy to take questions.
Just for the question, deliberate about how long you want to delay lunch. But
well, that's going to discourage questions, yeah.
So by sequential posted price auctions, you're allowing, I'm not sure what auctions means there, actually. So,
OK.
So you're allowing dynamic reordering of the subsequent people you consider in sequence.
Yes.
From based on what happens previously, right?
Sure. That's allowed, yes. That's about it. I mean, so yeah, I guess you can, if you go beyond this two-type case, you really, you can't condition much on on the fact that somebody just rejects a take it or leave it offer. So in some sense, you're allowed to condition on it, but in some sense, the mechanism builds that conditioning in what it's going to do next anyway. So really, it's the ability to choose the ordering that is the remaining degree of freedom here.
So the only information you get from someone is whether they took the offer. You can't get more information from them.
Right. You can ask them to report the value of the deliberation in a dynamically direct mechanism.
So then you can condition based on.
And then we could condition on whatever they tell us as the result of the deliberation.
So it's like the difference between knowing someone's value and knowing whether they.
That's right. It doesn't change things in this two-type case, but it changes things more broadly.
Prior free, for instance, approaches posted prices versus sort of online auctions are very different because you learn a lot more if you know the value of whether someone's.
Fair enough. And for that reason, you might not like the use of the phrase posted price. I guess it's still the case that agents are going to be responding to a single offer that they know what it is in advance. OK, thanks.